discussion after the presentation. Today we are featuring Kyle Hinson as he talks about extent and causes of Chesapeake Bay warming. Kyle Hinson is a PhD student at the Virginia Institute of Marine Science at the College of William and Mary, studying current and future impacts of climate change on Chesapeake Bay hypoxia. While working at US EPA's Chesapeake Bay Program Office, he helped incorporate climate change and atmospheric deposition projections to model estimates of future watershed nutrient runoff. This work continued when he entered VIMS as a graduate student and began applying modeling techniques to study the impacts of recent temperature trends, climate change, uncertainty, and nutrient reductions on bay water quality. Take it away, Kyle.
Awesome. Thanks so much, Kat. And thank you everyone for tuning in today. So as Kat just said, the title of my talk is The Extent and Cause of Chesapeake Bay Warming. And I want to first thank my co-authors, my advisor, Margie Friedrichs, lab members Pierre St. Laurent and Faye Daw, and then a committee member, Ray Najar at Penn State University, as well as funding support from both NOAA and VIMS. And this work that I'll be showing today has just very recently been published in the Journal of the American Water Resources Association. I put the DOI here, but probably hard to remember. So if you want a copy, just send me an email. It's also open access. So to begin, the history of warming in Chesapeake Bay is not necessarily a very new topic. It's been studied pretty extensively over the past 15 or so years. An estimate by Preston in 2004 pinned the average water temperature increase of approximately a degree Celsius over the latter half of the 20th century. Then Ding and Elmore completed an analysis in 2015 looking at surface temperature trends using satellite data. And they found that the temperature increase could range from about 0.5 degree to 2 degrees Celsius over an approximate 25-year time period. And then very recently, some former coworkers of mine at the Chesapeake Bay program led by Richard Tian in the same journal looked at how the change in water temperature from very near-term projections has modified Bay processes, and they estimated that there's an overall change of 0.85 to 0.9 degrees Celsius over a 30-year period. And then on the right here in this figure, I've just plotted a time series of average surface and bottom temperatures annually across the entirety of the bay from a whole bunch of different observation stations. And you see there's a warming trend that about matches a lot of what's been shown here on the leftmost axis. These are the average observed water temperature over the whole time period. So there's a slight upward trend. That's pretty well established, but it leads me to my main research question, which is to ask, what are really the relative magnitudes of these different mechanisms that are driving annual and seasonal Chesapeake Bay warming? And that hasn't really been addressed to date, but is talked about more in here. So when we think about the mechanisms that could be behind overall warming rates in the Chesapeake Bay, there are really 4 main drivers. So there's the impact of atmospheric forcings, whether that's through air temperature or the effect of downwelling long wave radiation as CO2 concentrations increase in the atmosphere and trap more long wave radiation. There's the effect of increasing river temperatures, which are altered by changes in the watershed. There's the effect of sea level rise, which can change the overall volume of the bay and possible circulation patterns. And then there's the effect of a warming ocean boundary, which is influenced by processes like along shore transport down from like the Gulf of Maine, and then what's happening with the Gulf Stream. So I'll step through a couple of these just to give a little bit of a better idea about what they've looked like from our analyses. So if we think about the effect of atmospheric warming, here I've shown this plot, the monthly air temperature trends in degrees Celsius per year over a 30-year time period. And on average, they've increased across the whole year by about 1/4 degree Celsius per decade. And what we see is that there's somewhat good agreement between these US Historical Climate Network stations, which are these filled circles, which are these long-term time series that have been corrected for all sorts of things that are very high quality data. Um, there's a good agreement between those and the background colors, which is this ERA5 reanalysis, which is a little bit different from the North American regional reanalysis, which is often used, but we found a better agreement with the data using this product. And it gives us a more continuous spatial coverage. And then we also see that compared to the cooler months from November to April, these warmer months from May to October suggest there's maybe higher trends in warming throughout the summer period. And then if we think about the effect of ocean changes that could affect the bay, my colleague Faye Dodd is a co-author on this paper, helped do this analysis on the left, showing the average monthly temperature trends near the bay mouth with these sort of standard error bars on the dots estimating the absolute trend in degrees Celsius per year, and also showing there's a little bit greater warming in warmer months. And then that looking at sea surface height, which is derived from tidal gauge stations at Duck, North Carolina and Lewis, Delaware, coupled with the AdCirc model, there's approximately a 17 centimeter increase near the bay mouth, which is a main driver of circulation changes and overall volume in the bay. So those are just a few of the direct sort of inputs to the bay that we analyze for our study. And then we also relied on this sort of vast Chesapeake Bay observing network to help really guide our analysis. So we compared some of our results to this long-term monitoring. For those who aren't familiar, since 1984, partners in Maryland and Virginia have gone out one to two times per month along the main stem here and other tributary stations. And they do lots of water quality sampling, also physical sampling like temperature salinity, of course, and also looking at dissolved oxygen. So there's this whole great wealth of data that we're able to use for our purposes as well. And then on the right, there's also a smaller network, but a more continuous record of observations since 2008 of sort of things like surface sea surface temperature or chlorophyll, also some real-time weather from these buoys that are deployed by folks all around the bay. And so that also gives us something that we can use to analyze. And while other people have looked at observations, we use this sort of observational data to help inform our modeling efforts. So for our analysis, we used this three-dimensional hydrodynamic biogeochemical coupled model called Chesrom's ECB, which is a version of the regional ocean modeling system, or that ROMS in there. And then the ECB is the estuarine, carbon, and biogeochemistry component. And this model, like I said, compares its outputs to data from these monitoring stations along the main stem for our results. And we also inform the model using atmospheric forcing. So we have this hindcast weather data, that ERA5 reanalysis I mentioned, that background color of the air temperatures, and it has all sorts of things like wind and humidity and radiation as well. We have coastal fluxes here on our model's ocean boundary. So this is sort of climatological data that's used to inform our simulations. And then we also have inputs all along the boundary of the river boundary of our model from the Phase 6 watershed model, which is provided by our partners at the US EPA's Chesapeake Bay program. And that gives us daily inputs of things like discharge and nutrient loads. And so this three-dimensional model has 20 depth levels. It has daily outputs of things like hydrodynamics and biogeochemistry. But for our purposes, we really focused on the bay temperatures that it simulated. And we ran this over a 35-year time period. And also we ran it for a whole bevy of individual sensitivity runs. So this next slide, I've described sort of the setup of our experiments to compare the long-term run, which we use to estimate warming, with these sort of individual drivers, which gets at the mechanisms behind the warming. So we do this because there's a whole lot of interannual variability. And by only applying different forcings to a shorter time period, we can remove that source of uncertainty from our estimates and really drill down on how much each of these different factors have contributed to overall warming over this 35-year time period. So we have a realistic run in the past from 1985 to 1989. We'll call that our base experiment. And then we use this thing called a delta approach, which is really like a 30-year estimate of change applied to that base condition and hold everything else constant. So for our first experiment, which combines all of these factors, we increase ocean temperatures, air temperatures, and long-wave radiation for atmospheric conditions. We increase river temperatures based on a literature estimate described on here. And we have our estimate of increase in sea level rise, as I described previously. And then we can step through each of these experiments individually and look at how these factors modify overall temperatures by themselves. So in combination, then, if we want to see the impact of ocean temperature, we'll only change ocean temperature and leave everything else constant, and do the same for each of these other experiments, moving down the list. So with that said, I'm going to jump back real fast to talk about what our model looks like when compared to observations over the entirety of the time period without looking at individual forcings. So this is a very busy plot, but I'm going to step through it just bit by bit here. So on the y-axis, we see this is the temperature trend in degrees Celsius per year per month over this 35-year time period. So when we ran our model from 1985 to 2019, we compared the temperature trends against observations. And so these red dots and error bars represent our best estimate from observations with standard errors of the temperature trend in a given month at the surface in the bottom, surface on the left and bottom on the right. And then this blue dot here represents our model results, but sampled at the exact same time and location as the observations. So we're sort of subsampling this broader estimate of model outputs and seeing how well they align with these observed trends. So if we had absolutely no model bias, if we exactly simulated observed conditions, the red and blue dots would align perfectly. But that's not the case. We've done some skill analyses that are described more in our paper and find that overall we do fairly well at capturing temperature and salinity, but I've neglected to include those slides in this presentation, but it's described more in the paper. And then this black diamond, this model ref all here, shows estimates of warming that don't have potential sampling biases, like the limitation for the frequency of measurements. Like I said earlier, they're usually sampled 1 to 2 per month in observations, or maybe there are weather limitations. Boats can only go out to sample bay temperatures when weather conditions are better, maybe after a storm, after the water column has been mixed. And there are other effects like that could alter measurements over time. And so we get a broader spatiotemporal sort of coverage using the black diamonds from our model outputs. And we see that they still align fairly well. It might be a little bit higher in some months compared to others. But overall, another takeaway is that there's greater warming at both the surface and the bottom in warmer months, which is on average around 0.3 degrees Celsius per decade, as compared to the cooler months, which averages out to about 0.1 degrees Celsius per decade. So that compares over the whole time period, accounting for things like interannual variability, estimates of warming from both observations and our model outputs. But the next few slides, I'll describe some more of the outputs from our overall experiments. So when we think about how all factors have warmed the bay, it's important to also consider whether there are any substantial changes between surface and bottom. And overall, if we look at this figure on the left, surface A and bottom B, this 30-year change in temperature, we see that they align fairly closely. There might be a little bit more warming in the bottom, in the southern half of the bay compared to the surface, but these are fairly regional differences, and overall they average out to approximately the same. And it's a fairly shallow system. On the right here is this main stem profile. So this dashed line here, this represents sort of a transect view of the bay. And you see that like some regional differences, but overall fairly homogeneous throughout the water column. And this comes out to about 0.7 degrees Celsius over this 35-year time period. And this is calculated using our combined experiments, so all these different factors applied and removing the effect of interannual variability. And then when we think about, well, this is an annual estimate, have these changed seasonally, we can say that, yes, there is substantial variation between months. So again, I'm showing that sort of transect view of the bay with the northern half of the bay on the right, and then it's closer to the bay mouth and the ocean on the left, and on the right is closer to the bay mouth. And for each month, we see that there's more warming, again, from May to October than there is in these cooler months from November to April. And there's some differences that are more pronounced in terms of surface changes versus bottom changes. But again, across the whole year, it averages out to approximately the same. And this makes sense with our understanding of the bay dynamics, and that over time, it's a fairly short residence time between like 6 and 9 months. So you wouldn't expect these temperature differences to get baked in over the course of numerous years. So I'll step through now looking at the effect of these different factors, both combined and individually, for the entirety of the bay. So in this figure, I'm showing an estimate of 30-year temperature change across the entirety of a given year for our combined experiments. So all those factors, including atmospheric conditions, sea level rise, ocean boundary warming, and river temperatures. And this is the bottom temperature change across the entirety of the bay. And what we see right away is that it's positive, which is unsurprising, but this estimate of 0.75 degrees Celsius is about what we've seen previously, but it varies a little bit between months. And again, there's that elevated warming from May to October and much less from November to April. And so I'll step through and look at the different factors of individual forcing mechanisms. So in this first one, I'm showing the effect of river temperature, which, although it looked like nothing changed, there's this little green line down here. And overall, this is telling us there's little to no warming in the bay's main stem that can be attributed to any changes in river temperatures over this 30-year time period. And then looking at the effect of sea level rise, we see that it has this slight cooling effect from April to September and a slight warming effect in the winter months. And this has been studied pretty extensively by a co-author of mine, Pierre Saint Laurent, who really looked at different things like fluxes and whether it was bringing in cooler water from the ocean. But in reality, this is analogous to having a pot of water on the stove. If you add more water to that pot, it's going to take longer to warm up, and it'll also take longer to cool down. So it really increases the thermal inertia for the bay. But overall, again, this effect is pretty small, and neither really seem to explain what's going on when all these factors are combined. Then we see the effect of increasing ocean temperatures, which are very important in summer warming, but have a pretty small effect otherwise. And this is averaged over the entirety of the bay, but as you might suspect, it actually becomes even more prominent near to the mouth of the bay and less so further upstream near the head of the tidal tributaries. And then lastly, I've added the effect of atmospheric temperature alone, which you can see almost exactly tracks the combined impacts over the entirety of the year, except in the summer when its effects are lessened due to this impact of ocean warming. So atmospheric temperatures are really driving the overall trends across the year and over a longer time period, but ocean warming has a not insignificant effect in the bay as well. And then plotted up on this slide, I'm showing the percent contribution to combined bottom temperatures for all these different factors over these warmer months, May to October. And the same story is here for the winter months, but I'll just highlight what's going on. So we see that the effect of atmospheric conditions really dominates the response over most of the bay, but to a much lesser degree here in the southern main stem, where the effect of ocean warming contributes a great deal, up to 80% or more during some of the summer months. And then we see that the effect of sea level rise has a slight cooling effect everywhere, And the effect of river temperatures produces almost no change except at the heads of these tidal tributaries. And quantifying this, you have almost a little over 3/4, maybe 85% on average over the whole year of the effect of warming is driven by atmospheric warming. Then we have 25% in the summer driven by ocean warming, a little bit, just about -5% driven by sea level rise. And then again, river temperatures do almost nothing. So sort of a summary of the research side of this talk. I've said before that the total bay warming that's been observed from and also modeled in our analysis shows an increase of about 0.7 degrees Celsius from 1985 to 2019, and that the summer warming calculated is about 3 times greater than that seen in the cooler months. We saw there was essentially no contribution of increasing river temperatures to overall bay temperature changes, and that during the summer, the effect of sea level rise can actually lead to a decrease of about 0.1 degrees Celsius. In the summer, the effect of the warming ocean boundary can contribute to half or more of the total warming in the bay. But the vast majority of the warming in the bay is driven by these atmospheric changes. And so in the future, when we think about what's most important to warming processes, it's really important to think about how the atmosphere will continue to change, as well as the effect of what's going on offshore and bringing that sort of oceanic influence into the bay. Although the effect of sea level rise, if it accelerates, could potentially be important too. And so there's a few management implications for some of these findings. Reducing river temperatures throughout the Bay watershed is highlighted as one of the goals in the Chesapeake Bay Watershed Agreement to help improve things like brook trout habitat, sort of shading these smaller order streams, but it has very little likelihood of having any effect on main stem bay warming, where there are big impacts like dissolved oxygen that are also under a lot of study, but they're still important for those stream health outcomes that I just described. And then if we want to think about the detection of future warming trends, our results might help to inform maybe the site selection of a profiling sensor. And we've actually also discussed this a little bit with Peter Tango, who's heading up the monitoring team at the Chesapeake Bay program as well. Some other work that's been done by a former lab member who just took a job with Epi Environmental, Luke Frankel here, and is about to wrap up his master's degree, has looked at the effect of nutrient reductions in the bay and over time, how that's really affected hypoxia. So I'll step through this graph bit by bit. So on this upper left figure, this is showing the annual hypoxic volume. So the amount of volume in the bay that's affected over the course of a year, has a sort of weird unit of kilometer cube days, but sort of the entirety of the bay that's affected by hypoxia in a given year for oxygen conditions less than 3 milligrams per liter, which is important for a lot of species. And then on the bottom, he's showing average discharge across the entirety of the bay watershed into the bay over the same time period. And we see that there's a lot of interannual variability. And he chose to really focus on the first like 4 or 5 years and the last few as well, to see whether over time we've had increased resiliency from nutrient reductions. So there have been lots of efforts to reduce things for nutrient loads from point sources as well as non-point sources, with more success. And even though 2018 and 19 were very, very wet, anomalous years, was hypoxia really as bad as it might have been in the 80s? So that was the focus of his work. And here he's plotting sort of this average discharge against this annual hypoxic volume on the y-axis. It has this sort of linear trend, and these red dots represent the earlier time period, and the blue dots represent the later time period, suggest that maybe there is a response to nutrient reductions. And so for his analysis, he found that there was a pretty big effect. So these are these later years. Again, this is all from Luke's work, showing the change in hypoxic volume. due to the effect of nutrient reductions, and also he quantified the effect of temperature. So these positive values sort of indicate how much worse hypoxia would have been had it not been for nutrient reductions. And then the gray bars down the bottom sort of represent how much that's been offset by warming that's been observed since 1985. So even though progress has been made, approximately 25% of the hypoxia that would have been limited without this warming increase has been. So we're sort of being held back by the effect of warming, and it's possible that this might continue to grow in the future. It might be more than what we've seen so far. And then lastly, this really ties into overall management implications that I've just discussed. On the right here is daily nowcast, and we also do a 2-day forecast at VIMS. This is Margie Friedrichs and Aaron Beaver's work looking at hypoxia in the bay, where red indicates lower oxygen waters, and then the blue represents healthier waters. And past work has really demonstrated by Wenfei Ni et al. At UMCs that increasing temperatures have limited the attainment of TMDL, or total maximum daily load goals. So there are a whole bunch of efforts throughout the Bay watershed to limit nutrient reductions, and in her analysis, and also as in Luke's analysis I just showed, temperatures are really hindering progress and reducing hypoxia. And then Richard Tian's work that I mentioned previously in the PowerPoint showed that increasing warming is sort of helping to drive a decrease in oxygen solubility, an increase in biological rates, so things like remineralization, and an increase in stratification, all of which can negatively impact hypoxia in the future. And then see to other questions like what % of hypoxia is attributable to the impact of anthropogenic warming? How much of it is due to the effect alone of natural variability? Things like maybe the AMO is altering these long-term warming patterns, but that's a question for another talk. And it's the end of mine. So if you have any questions, feel free to email me. Here's my email below. And with that, I will take questions now. Thank you so much for your attention.
Thank you so much, Kyle. It looks like we have a couple of hands raised. Grant, I see you. Did you have a question?
Yes, hi, Grant McCardle, University of Connecticut. I'm not surprised that changing the temperature of the riverine inputs has little effect, just because, the volume compared to the total volume of the bay is, small. But did you look at changing the discharge? Because I might expect that to affect the heat exchange between the bay and the ocean.
Right, that's a good question. We, not exactly in sort of like a heat flux analysis, but again, there's that really high level of interannual variability, which I think could be impacted by things like discharge. But for our analysis, we really removed that effect by doing these 5-year simulations with the delta of these different effects added on. But yeah, that's a good question. Is long-term increase in something like discharge potentially going to affect warming? And I would argue that it would probably need to be substantially greater to modify what we're seeing due to the effect of the atmosphere, which is a more consistent trend. Thanks for your question. I hope I answered it. Are there any other questions? I might have talked fast.
Oh, you mean for me? No, that was it.
Oh,
thank you.
That's right. In general, yeah, thank you.
Hi, this is Roger Stewart with the Virginia DEQ. I had a quick question for you.
Sure.
We've started to take a look at the photosynthetic active radiation measurements at the surface. we have measurements that go back quite a long way, back into 1985. And I've seen a slight trend in increasing amount of radiation. Have you taken a look at that as possibly a driver towards temperature increases?
That's a great question. I haven't specifically, but I think that it ties in well to one of my colleagues, Jessie Turner, who also recently graduated, in her work. So she's looked at things like changing water clarity, which can help to increase phytoplankton growth throughout the bay. And that was, it's important sort of in the mid region of the bay outside the estuarine turbidity maximum, but also Grace Kim has recently put out a paper, I think maybe the end of last year, looking at how whatever's in the water column at the surface can differentially affect warming throughout, or affect temperatures throughout the bay. So yeah, exactly as you're saying, what sort of light attenuation helps to increase maybe bottom warming more than surface warming. And yeah, we've seen in some of our analyses, you know, some parts of the bay do better, but we don't have this sort of regionally variable light attenuation in the surface of the water column. But that, yeah, it's something that could be interesting to look at more.
Yeah, what drove our interest was that when you take a LICOR measurement, you take a surface measurement and then you take the measurements at depth. And we only concentrated on just the surface measurements to see if there was an increase in the amount of radiation coming in. We weren't so much interested in, how deep it penetrated or water clarity, but we said, let's just take a look at what the background radiation is reaching the surface, and we've seen an increase in that. And it kind of goes along with this anecdote that all of us old timers feel like, is the sun a lot stronger than it used to be, or are we just getting older?
Yeah.
Is it just more affecting us? But there are a lot of people who say, the sun seems a lot brighter than it has been. And I don't know if there are any other studies where they're looking at, what is it, the micro Einsteins per whatever per
Right.
square meter. But it might be an avenue that could help explain some of the surface temperature increases.
Yeah, it's an interesting question. I mean, I looked at some changes, or try to fit trends to shortwave radiation measured, which are fairly sparse throughout the watershed, and didn't find very sort of significant trends. I don't think that the 11-year Milankovitch cycles of the sun have been changing so much, but I can't truly speak to whether or not the bay is getting less cloudy. It's the only other thing that I could think of that might alter PAR.
Yeah, that's a good point.
Yeah. So, but yeah, thanks for the point. That's really interesting. If you have no other questions, Roger, I saw, I think, John Wilkins' hand go up first.
Yeah, thanks, Kyle. This follows a little bit on from Roger's question, actually. I assume in your model configuration, you're using a bulk fluxes algorithm for calculating the SE
Oh, what?
A bulk flux parameterization for heat fluxes. You're not imposing the fluxes directly from ERA5. Is that right?
Right. Yeah. It's
So have you, or has anyone sort of delved into which part of the SE heat flux is driving that warming? Is it latent heat, sensible heat, or in fact changes in the shortwave radiation?
When I have looked at this, I'm trying to recall. I think that I may misspeak. I thought it was the biggest driver was latent heat flux. And I should note that the atmospheric warming effect we see is, again, not just air temperature, it's also long wave radiation, which accounts for maybe 0.2 of the 0.6 degree change. But I don't think shortwave radiation was one of the bigger factors. I can't remember exactly, I'm sorry.
Okay, thanks. Shortwave is one of the things that these analysis products do most poorly. because of poor cloud parameterizations and aerosol effects. So
That's really interesting.
thanks. Yeah.
Thank you. Blake, I saw your hand up.
Yeah, can you hear me okay?
Yeah.
Okay, sorry, my mic isn't great and my video isn't on, but yeah, thanks Kyle, good talk. So to go back to the PAR, just off the top of my head, I was thinking maybe just long-term decreases in atmospheric pollution might have caused an increase in PAR as cars have become more fuel efficient. Just a thought off the top of my head. But my question was, in your climatological analysis, obviously January stands out as like a big outlier in the winter months in terms of temperature anomaly or temperature increase. Have you thought about why that may be, or were there specific years in the data set where like January was just like anomalously really warm, that if you excluded those years then it would be more in line with the other winter months?
Yeah, you mean January or December? So like here, January is sort of coming down from the 14 in.
Yeah, okay, sorry. December into January.
No, that's a good question. I think that 1985 overall was colder than some of the following years, which might sort of bias the trend, but there were also the trends in water temperature were calculated using an autoregressive model of order one, trying to sort of account for things like that. As far as what could be driving, I didn't see a whole lot of anomalous years. Here, I'll show a quick example, this extra slide I have. So this is November temperatures, which showed cooling, which also matched some estimates that Jeremy Testa put out a few years ago. And you see that, yeah, 1985, sorry, it was more warm, I was mistaken, than anything else. This is just November, and this is air temperature down below and ocean temperature on the left. But I didn't see any good reason why November should be cooling more and December should be much higher than the others in the winter months. I've been asked a lot before about why November is so cool, and I don't know if it has to do with some kind of changed atmospheric pattern, but that's not my specialty. And it's just really what the data appear to show right now. So right, did that answer?
Cool, thanks. Yeah.
Were there any other questions?
All right. Doesn't look like there's any other questions. I'm not seeing anything in the chat or anything. Thank you so much again, Kyle. We do have a few other speakers signed up for the summer, and we will send out that login information in the next coming weeks. If you or someone you know are interested in doing a science talk, please contact Mary Ford. Her email address is mary@maricruz.org, and we will get you on the schedule. Thank you all for joining us, and thank you again, Kyle. This was great.
Thanks so much, everyone.
Thanks, Kyle. This was fantastic.
Thanks.
Thank you.